Oh, sorry. Yes. There's a seat over there, but if you want to check it out. Oh yeah. And it's gonna be about something about forbidding even cycles, right?
Yeah.
Please.
Hello. Thank you for coming and having me here. So as we had an amazing talk by Zhen last week, and he's inspired my talk for today, and I changed my plans. I will start gossiping about him also, this talk, and I want to say that I'm very happy of his talk because I will base my talk on things which he already said, but at the same time I will have some repetitions, and sorry for that if somebody will be bored by hearing something second time on the second week, but mainly everything he said I will be using and stating those things. So today I'm gonna speak about generalized Turan problems, and as you have seen, the first thing is that since I liked his talk, I little bit changed my plan. My plan was to talk about one of my papers, which is recent, but now I decided to make it a little bit more general. Okay, so as you remember, last week we defined what was extremal number, so-called Turan number, which is denoted by Ex and H, which is maximum number of edges in the graph with n vertices such that G is H free. So what does this mean, G is H free? It means that G does not contain H as a subgraph, not necessarily induced. So how do I see this thing? I can just little bit rewrite this problem, this definition, and instead of writing Ex and H, I can write, for example, here Kn. So you can see that we have a Kn, the ground graph, and you are searching for the subgraph of that given graph with the property that you don't have an H as the subgraph. Or
should it be a spanning subgraph?
Not necessarily. I mean, you can take isolated vertices. So
Okay.
yes, that's a good question, but yes, maybe if I really, maybe I can change this here. Yeah. So I'm just hypothetically thinking about this. Or instead of saying that Kn, I can give you a class of graphs, and I can tell you that please find the most number of edges without H in this class of graphs. For example, what can be this class of graphs? It can be all connected graphs on n vertices, or all planar graphs on n vertices, so on. So this is some possible ways of generalizing this number, and many people have done research towards that direction, but today we have some other plans. Okay, now question is, find Ex and H. What does it mean to find it? We can sometimes find exact number, or sometimes we are not able to find an exact number and we are asked to find asymptotics, or at least to find an order of magnitude. Depending on H, the question has, I mean, we have different possibilities. For example, you gave me H for which I determined exactly this number. What can be the next natural question? Next natural question is to find Ex and H. Let me not write the definition for this. This is a class of the graphs for which we have n vertices, no H as a subgraph, and exactly as many edges as this much. So not only we determine that extremal number, but we can determine sometimes extremal graphs. What can be the next step? Next step is that, okay, maybe we don't have as many edges as this much, but we have almost as much. Are we close to this family? I mean, what does it mean close? There is like the stability, also different topic, we don't discuss it. Okay. The other possibility in here can be that no, not we have less, but we have more. But this guarantees that we will have an H. But do we have one H or we have many H's? So this is also a very nice topic. Let me still stick to this topic because of this is the topic which inspired today's topic. Therefore, I want to still repeat some classical results. The first result comes from 07 by Mantel. This is more like an example to understand what is this function. So it states that extremal number on n vertices without a triangle is n squared over 4 floor. And extremal class is just one graph, complete balanced bipartite graph. So this is n half floor, this is n half ceiling. So what is this? It's trivial to see that there is no triangle, right? Because there are no odd cycles here. So the first observation is that just forbidding a triangle gives the same extremal number as forbidding all of the cycles. So here comes another generalization of this question. Instead of forbidding just H, maybe sometimes makes sense to forbid some family of the graphs. And the requirement is that you want to find an n-vertex graph without any H from your class of family, forbidden family. So, and this was the first question, and one of the, I would call, main solved problems from this topic was motivated by this problem, so we will see this a little bit later. Okay, so let me leave some gap here and continue. In 1941, this is the beginning of this era, beginning of extremal number and everything. Turan proved the following theorem, generalize this. So what is triangle? Click on 3 vertices. Turan proved that Ex n k t k plus 1 is Turan number on n vertices and nt. I need to define this. Okay, what is this? Sorry, okay, that's true. So, okay, this is a Turan number. So Turan number is n.
This was also the Turan number.
Okay, cool. Size of the following graph. This is a Turan graph. Size means that number of edges. Okay, now I need to describe this graph here. So we have independent sets. Each independent set is size roughly n over k. What does it mean roughly? It's either floor or ceiling. So we have the graph composed from the independent sets. How many of them do we have? K of them. And we have all edges in between. So this is a blown up KK. We just blow up KK, where for each vertex we take independent set of size n over k. The only goal is to have n vertices, so this is the only one way to find it. How many n over k floors do we have and how many n over k ceilings we have there. So this is our Turan graph. And Turan theorem states that if we have more edgings than here, then you must have a clique on k plus 1 vertices. And why don't we have a k plus 1 clique here? Because by pigeonhole principle, there will be two vertices from the same class, and then there is no edge in between. So this theorem is well studied, many ways generalized. Okay, so when here Erdos found this problem very interesting and saw the potential of generalizing and studying this subject. So generally this extremal theory was really studied by Erdos a lot. He felt sorry. Why he felt sorry? Because he remembered that in 1938 he had this determined ENC4. Not exactly, but he had some lower and upper bound, and this was the problem. He was studying the following problem. Imagine that you have a subset of integers from 1 to n, and you don't want to have a solution for the following a1 times a2 from b1 times b2, where a1, a2, b1, b2 are from a, and obviously these two are not the same as that two. And you don't want to have a solution, and what is the maximum size of a? This was the question, and he comes up with the solution, and for that what was needed, he needed to determine this number, he does it. And this was also the first time when someone used the finite geometry to construct the lower bound for such number. So to find a lower bound, you always need some construction, and to find an upper bound, you need some proof. So I'm not gonna write anything about this here. So this was maybe first real result from extremal graph theory, but unfortunately, as Erdos mentioned, he missed it, and then Turan found. So here comes the fundamental theorem, in many opinions. So this is two papers, Erdos and Stone, and Erdos and Simonovic, and I will just write one year. So this is EX and F is n choose 2, 1 minus 1 over chromatic number of F minus 1 plus O1. So more or less this theorem settles all of the problems, at least asymptotically. So this states that
non-bipartite.
yes, we will,
Okay.
more or less. Not yes. I will say that comment soon. So first, let's describe what happens here. This says that whatever you forbid f does not matter. I mean, it behaves as if you have forbidden the complete graph. Okay. And one question is the following, that if the chromatic number is given, let's say the chromatic number is k plus 1, obviously the lower bound is this one. And for which graphs is exactly this one? For which graph we cannot add any edge. And there is a very nice theorem of Simonovic. It states that if the graph is edge critical means that there exists no edge after removal of that given edge, the chromatic number decreases, then the extremal number is strictly more than that. Why? Because you just add the one edge here, and it's done. And he proves that this is the class. So every other class must have extremal number at least 1 plus. Okay, so as already mentioned, yeah, I was cheating when I was saying this settles everything asymptotically only if the chromatic number is at least 3. If chromatic number is at least exactly 2, then this says that it's subquadratic and we don't know anything. So today there is extensive study for this, and my talk in that direction is finished. Please refer to his talks from the last week about the bipartite graph. So now comes the natural question. When you define Ex and H and you want to maximize number of edges, why edges? What is special about the edges? Why not other structures? And yes, this is the generalization which we want to talk. So once more, F is forbidden. That's why we have chosen F, forbidden. This is maximum number of H's in G. So let me say that this is a function which counts number of copies of H in G, where vertex set of G is N and G is F3. So what does this mean? Ex and F is the same as Ex and edge F. Okay? So, as I promised, I said that one of the main questions, solved questions in this direction is from that problem. So, as you have seen that we forbid the triangle, we got a bipartite graph. So Erdos naturally asked the question, how far are they from each other? So how close are the bipartite and triangle-free graphs? And he asked many questions, and the question was the following. Can we prove that Ex n, so we forbid triangle, and we don't want to be bipartite. So let's count another cycle, pentagon. And this was the conjecture that this is n over 5 to the 5. Let me, I just assume that just not to be, this can be for every n, but let me just write for n divisible by 5, otherwise I can start writing the floors and ceilings. So just to be simpler side, I'm speaking about this. So this was the conjecture, and the construction was the following. You just take a C5 and you blow it up. So each class has size n over 5, and you have independent set of n over 5 vertices, and it does not have any triangles. And this was a conjecture of Erdos, which was, I don't want to spell wrongly the names. It's here. Solved in 2012 by Zheshik and independently by Hatami, Platki, Kral, Norin, and Rasborough. Yeah, it's a good guess by flag algebras. So I think one of the first biggest application of flag algebra was this problem, and this problem was solved. So this was just a commercial of this topic. That's why maybe I started with this. So maybe for some people this talk will be here and there because of somehow I want to show some results with not consecutive order. So before this problem was solved and this problem was still open, Bolobash and Győri asked the following question: what happens if we not forbid triangles? We will count the triangles and with pentagons. And they come up with a very interesting construction. For the construction, so they prove first of all that this number is at least 1 over 3 root 3 n to the 3 half. So maybe this number for the extremal graph theorist now does not tell anything, but that's why let me rewrite this little bit differently. This is 2 root 2, 2 over 3 n to the 3 half. Now I guess everybody can guess what is the construction who works in this field and who attended the last talk maybe. So last week we have seen that if we take a bipartite graph C for 3, then there is a construction such that the number of vertices here is n over 3 and n over 3 and some edges, not complete. So this is independent and this is, let's say, G. A number of edges in G is something like 1 over 2 root 2, number of vertices here, which is 2n over 3 to the 3 half. So, and G is C for 3. So we have seen that construction exists. There are many beautiful constructions. Actually, this is one of the nice topics to discuss with the student in general. So we had this construction. Okay, so they started with this construction, and now we need to make a graph which contains n over 3 vertices more. What they did, instead of each vertex upstairs, they took an edge. So they took instead of a vertex, they took 2 copies of the same vertex joined by an edge. So I don't know how to draw this picture. Anyway, I think the construction is clear, right? So instead of every vertex, you take a copy of that vertex joined by an edge. So what we get has many triangles. How many triangles? Every edge was transformed to the triangle. So number of triangles here will be exactly this much. Now we need to show that there is no pentagon. Assume that there is a pentagon. So if in this graph there is a pentagon, you need to at least use one red edge. But it is easy to see that you cannot use more than one red edge. And if you have one red edge and every other white edges, your pentagon looks like that. But remember that these two vertices has the same neighborhood. So these two vertices initially was a vertex, this another vertex, and that's the C4. So this means that that graph is definitely C5 free. So this is a nice lower bound. This problem had lots of upper bounds. I mean, like, of course, all of us in Győri had an upper bound, and Furedi, then Alon, and so on, many people. Then I had also upper bound with other co-authors and Ervin. And right now there is a paper which is not available, but I know that there is an upper bound by you. This is the paper which is submitted but not on archive, and as you see, this is the constant root 27, and their constant is 1 over root 24 and to the 3 half. So there is still a huge gap here, and I'm interested to work about this problem, and I have studied this paper, and I know how to say, they use some famous inequality, and if you use that inequality, you cannot get better. So they do the best after using that inequality. So the question is, maybe we can improve that inequality, and I'm really interested to work on this, and I have some ideas about that, so maybe we can discuss this some other time.
That's a still lower bound, right?
Yeah, that's an upper bound.
Upper bound, okay.
Sorry, I'm sorry. Yes, this is an upper bound of Ex and this. Okay. We conjecture that this is the correct. Yeah, one thing is that everywhere here is small o missing. Here and here, we small o and to the 3/2. So yeah.
Is
So
getting the 3/2 in the exponent easy in the upper bound? Or
sorry?
is getting the 3/2 in the exponent easy?
I have a paper with Ervin, Becca, Ergemlidze, and Mesuku where we prove 1/2√2 and to the 3/2, and I can do it in 5 minutes after the talk to you. I mean, I can even say now, but to prove 1/2√2, it has a very beautiful, nice proof.
Okay.
But we use some famous theorem, but this result is based on. I'm sorry, I forgot. I think it's only Shimonovich's theorem about the number of edges in the graph which does not contain any C4 and C5. So we use that. We know that's number. No, C3, C5. Okay, so see. So this one, we use this extremal number. So this extremal number is also very interesting because everything is determined except C4 and every odd cycle we know. The only thing we don't know C3, C4. So this is also a very interesting topic here. Yeah, I'm happy to show this proof some other time after this talk maybe, if you would be willing to listen. Okay, so one of the first papers in this direction is the following paper of Győri, and Shimonovich. So this is not only the start of this topic, but also beginning of my life. So we have H, which contains almost most matching. So what does it mean? It either contains a perfect matching or it contains a perfect matching and one isolated vertex. So H is such. And the question is this C3. So far I would draw a drawing triangle. So what is this number? And this number is number of H in so H is bipartite. In Turan graph. What is Turan graph? This is this. T and 2. Okay, so this was proved. Somehow many people want to generalize this theorem for something, and that's very hard. Very hard meaning to make a sensible conjecture. We will see why. So the first conjecture. Liditsky, Murphy. Assume that R is greater than chromatic number of H. Then there exists N1 and R minus 1 such that extremal number of N, H, K, R. So instead of triangle, they forbid a complete graph on R vertices, and we want to maximize H is H, K, N1, N2, and R minus 1. So it says that if you want to maximize H in KR free graph, instead of a Turan graph, maybe it's still the Turan graph, but it's not balanced anymore. Like you need to find some different sizes. Maybe that was the conjecture. And this is a very cool conjecture in the sense that if it would be true, it would solve many problems because of using graph removal lemma. It is trivial to prove that extremal number. So this is correct, and this is like easy to prove that HF is at most extremal number of NHKR plus ONV of H. So if we have this, and if we would have that, then this would asymptotically solve all the problems, and that's why this conjecture was a very cool conjecture, but unfortunately this is wrong. Okay, why it is wrong? Recently, by Győri.
Sorry, when the thing that you wrote, F can be any graph. Is that what you mean? Just below Y.
Yes. Yes, the chromatic number of F and chromatic number of H. So as
Probably you mean chromatic number of F equals to R, right?
yes, that's correct.
What is VH? OV.
And R is greater than chromatic number of H. Thanks. So
Tompkins, what was the question?
I mean, the small old term, I confused about this VH, the definition of this VH.
So this holds when we have the condition on the chromatic number.
I think Tompkins is asking.
About the small old terms, I mean, what is the exponent means?
Number of vertices of H.
Number of vertices of H. Just for
I think that there is some theorem which I need to write it, and then maybe this will be more clear. So this was just a comment about why this conjecture was important conjecture if it would be correct, but Győri, Győri, myself, and Tompkins proved that that was wrong. And let me give you a construction. H is P to R to the R minus 2. What is P to R? Let me give you an example. R equals to 3. So P to R is a path. 1, 2, 3, 4, 5, 6 vertices. So this is P6, P to R. And then to the R minus 2, what does it mean? That we need to take any two vertices and connect them if the distance between them in P to R is at most, R minus 2. Since R equals to 3, that's 1, so that will be the same. So maybe we should check the other example. And here we need to plus do something. So what do we do? Instead of taking these leaves, we just blow up the terminal vertices. So H is P to R to the R minus 2, blown up with the blown up leaves. So sizes of this is A, and that is A, and that is given in the paper exactly what they are. So for R equals to 4, we take P8, 1, 2, 3, 4, 5, 6, 7, 8. And then what do we do? Like R minus 2 is 2, so we need to connect every two vertices if they are distance 1 or 2. So we do this. And instead of the terminal vertices, we take many copies of them. Okay, and this is our H. And what is the goal? To show that number of these in any such graph with any weight distribution is less than somewhere else. Now my goal is to show you where is this. This is cycle of r minus 1, and the degree is r minus 2. Blown up with epsilon n, and one big class. So what does this mean? So we take a cycle. Let me draw for r equals to 3. For r equals to 3, cycle length is 5. 1, 2, 3, 4, 5. Instead of each class, you take epsilon n vertices. And the rest, big class here. And you take all edges here, there, 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 and there. And we claim that if you smartly choose A and epsilon, the number of copies of this in here is more than in any of those graphs. Let me give you just an idea why it happens. Because this is uniquely colorable with r minus 1 colors. So no matter how you color it, this set will be red, and this set will be blue. Therefore, they will be mapped in the different classes. So the maximum number of choices for those vertices will be roughly n half to the 2a maximum. While in this graph, you can map these vertices here, then go around and map the blue vertices there, and this will be roughly n to the 2a. So this will be more than that, and even if for each of these vertex you have n choices, the number of them here will be much more than the number of them here. So it's just the calculations. So when we did this, my question was, okay, for triangles, let's prove it that it's either this one or that one. And immediately we had some counterexample for that, and that counterexample you can find it in the paper. So that we included that because of we believe that somebody would really also try to prove that, and that was also okay. So and instead of that, we came up with a new conjecture. So conjecture, I will not rewrite the same names. So diameter at most 2 r minus 2, chromatic number of G is at most r. Then extremal number of n, g, k, r is extremal number of this is number of g. Actually, so far I had h everywhere, right? K n1 n r minus 1. So this was our conjecture. Even more, we tried to prove this conjecture for r equals to 3, and we failed it. So we could not prove it, but instead of diameter 2 r minus 2 is 4, we tried to do radius 2. We did the radius 2, and we confirmed that that conjecture holds for not only the radius 2 but little bit bigger class. So what is the radius 2? You take this one vertex, so you take a star, and then you take some vertices which are hanging on here. Instead of the star, you can start with some complete KST, and you can start adding some vertices to join to any number of vertices on one color class. So here we started with the star, and we can start with any KS. So this is little bit a bigger star. So if H is reduced to or little bit bigger class, this conjecture holds for R equals to 3. But we could not prove it for all diameter 4.
Isn't it in that example the diameter less than 2r minus 2?
So this is for example we just chose the diameter from this construction. So what is the diameter of this graph?
2, 3, 4, 5, 6.
So this is
Okay.
2r minus 1. So these are 2r minus 1 vertices in the path. So diameter is 2r minus 1. So we say that if the diameter is less than that.
But for r equals 4, now in the construction the diameter is only 4, right?
1, 2, 3, 4,
The r
5.
equals 4 construction.
No, 7, which is also 2r minus 1.
Yeah.
Okay. So, and it happens that this conjecture was also wrong. And I found a paper, very recent paper, which yet does not cite our paper on Google Scholar, even though they cite us. So it's very new. That's why I just happened that I found it yesterday. Here. And they proved that this conjecture is wrong for every r except r equals to 3. So this confirms maybe why we could not prove it r equals to 3 for every diameter 4. But okay, anyway, I think that here needs to be either proved that there are other graphs for which this does not hold for diameter 4, or maybe at least for r equals to 3 this conjecture holds. I don't know. So this is the place where I want to stop here, and as I have seen my time is running up, so maybe I should go to the statement which I have stated in abstract, and it's time to talk about what happened in the past, even though there was a lot I wanted to talk, and speak about what was new and what I wanted initially to talk about in this talk. This is the result with Győri. You? Tompkins? Varga and Zhen. So we try to work on some problems about the cycles. So generally, these problems, if a blown up of H, so where is the definition of? Okay, if the blown up of H is F3, then we have how many copies of H? We have as many as number of vertices. Sorry, n to the number of vertices. So asymptotics is known. Therefore, the questions are interesting when the blow up of H is not F3. Therefore, the questions are very interesting when we are forbidding one cycle and counting the other, or complete bipartite graphs. Therefore, we studied the following questions. and we got exact results everywhere. Now, before we cycle of length 6, and we count the cycles of length 4, and this is exactly n minus 2 choose 2, and this is obtained only here. Complete bipartite graph of sizes 2 and n minus 2. This is 6 times n minus 3, choose 3. So this is the same. So here I write bipartite, so this means that we are considering n vertex bipartite graphs. So that's a Zarankiewicz problem. And finally we have two general results for not bipartite. Here we have the same number, but we can do +2, which is 2 vertices upstairs and -2 downstairs. We have one edge up, one edge down. This is +2 and all edges in between. So +2 means +2 for C4s, but we add these two edges, and that two edges gives you that +2 of the number of C4s. And about this one, this is n minus s, choose s. So in this case, we don't have +2 because of you can add only these two edges, but adding these two edges does not give you any new KSS. So as you see, C4 can be written as K22. So these two are the same theorem, but there is this +2, that's why we separated them. And I think I have some time, that's why I rushed to write those theorems. Let me give you some idea how we can prove the rest. I mean, they are using some induction, some progressive induction, and the different methods here, bijections between some sets, but we started everything from this, and this has a very nice proof. So we have a bipartite graph. We want to maximize C4s. Where is no C6? Okay, I have a C4. Okay, assume that I have a C4 on these two vertices. This one. Maybe we have another C4 when these two vertices are opposite. So this means that I must have another vertex like that. Do we have any other C4 on these two vertices? Maybe. So if we have this, then this is a C6, right? What if these two vertices are the same? They cannot be the same because the graph is bipartite. So if there exists another cherry on these two and another cherry on these two, we must have a C6. So this means that in every C4 I can choose a diagonal on which there is no such vertex. So let's start putting those edges. For each C4 I have a unique edge. In the end, the red edges is as many as the number of C4s. So what do I know? The edges which I was adding, we are adding in the same color class. So these are of same color class. So the number of edges we get is at most x choose 2 plus n minus x choose 2, where x is the size of the color class if we are in the bipartite graph. So we are somewhere in the bipartite graph. I don't know what is x. This was some graph which was C63, and then we started adding red edges. We add here, there, there, there. So finally, this number is maximized when x is minimum. And x should be at least 2, because we want to have at least one C4. So this is maximum when x equals to 2. And that gives you n minus 2 choose 2 plus 1. But it is clear that if x equals to 2, then you don't have that plus 1, and if x is greater than 2, this number decreases. So we got these results. In some cases, for example, in this case, it is not true for every n, so we need the beginning of the induction, therefore we could not find the base case, therefore we proved it with progressive induction, so that it starts somewhere around 3 times 30 choose 4. And this is about the bijection proof, therefore this is proof for every, no, this needs also some lower bound for n is large. I think my time is up. Thank you very much for having me here, and please ask any questions.
Okay, questions?
Okay.
How large is that?
Sorry?
How large do you require n to be? Like
In here, so in here,
oh, we have a number.
n is 3 times 31 choose 4. We did not really try to push this down, and here n is at least 3s plus 1 plus 2s plus 1 choose s times s half. So where is this coming from? This proof very much looks like that proof, but in that case, if we have that and that, we may have the following, that we have KSS, and we have one vertex which is joined to everything. So this is an object which gives us lots of problems and which contains many KSS. So if it is KS 2s plus 1 contains lots of KSS. So this means that when n is very small, this is not a construction. This is the construction when we have s and n minus s. Therefore, also in this theorem we need some base case. I mean, we need the beginning, but the proof is not about induction, so it's about finding some bijection between the sets of size s and KSSs, like here. But here it was great when we knew that the graph is bipartite and each edge was in the color class. But as soon as you say that it's not bipartite, I mean, this theorem is the same here, right? It's much harder. I mean, it's several pages wide. That's like one paragraph.
So can I ask some vague questions?
Yes, please.
In the examples that you showed us, like a Turan graph and then others, they feel more like a blow up of some existing graph and maybe add a few more edges. So are there any different types of extremal graph which have a different flavor? Not blow up, but some more other kind of patterns that can appear.
I don't have in my mind about the generalized.
Projective plane doesn't look like that, right? Projective plane doesn't look like that.
Yes, true. No, I mean, that's what I was saying, that for the generalized Turan graph, Turan problem, I don't know, but in the extremal problems, the lower bound comes lots of times from the geometry, or yeah, for example, this one also was given. I mean, if it's extremal problem, but right now we are in the beginning of this generalized Turan problem. Therefore, we are trying to solve the first questions where generally the things are blow-ups. Yes.
Can I ask one
Yeah.
more? So you also mentioned about capital EX, which are the solutions of this extremal problem.
Yes.
Do people study what kind of structure that solutions may have? Sometimes unique and sometimes they have.
Yeah, we study that, and we study the stability problems also. That meaning, if you are close to the extremal number, how close the structure is. And generally, those theorems are the most important theorems in the sense that those theorems have applications in some other problems. And generally, when you want to have some result in the extremal theory, it's about the stability more than the exact results and the flavor.
So for your theorems, you also also have a stability theorem?
No,
All four or?
no, we have not thought about the stability version of those theorems.
I see.
Yes?
So I guess in this first result, you can replace C6 with this specific 6 vertex graph that you've drawn on the right?
Sorry?
In the first result for this extremal number, for counting C4, C6 free,
Yes.
instead of excluding C6,
No.
you could exclude this.
We don't know. They are very strange. We can work on that problem. It's
Wait,
very confusing. Even, I mean, we could not even step from here, from, for example, 8 and 10.
The one with the
Yeah.
red and the X.
Yeah, why isn't it sufficient to put it in the picture on the right?
Sorry? This one?
When you found C6, you found a larger graph.
Yes?
So if you forbid that graph instead, I'm saying, so the
Instead of C6, you do this, what is it, octahedron.
Ah! Okay, sorry, I thought the question was for C8.
No. I mean a 6 vertex graph, but a slightly larger 6 vertex graph. And you'll get the same result.
Yes, true.
Is it known that you can define Turan exponent as the number that you can realize as x theta of m to the alpha, right? When you give a, so you have extremal number n h f, right?
Yeah?
Extremal n h f. Now I allow you to take f to be a finite family instead
Yeah.
of a single graph. So you can forbid a finite family. Now I say a number is a Turan exponent if there exists choice of h and f such that this number equals to big theta of n to the alpha.
Okay.
Now my question is it known that for every rational number
I don't know.
bigger than 1,
That's a good question. But this question has an answer here, right?
between 1 and 2, yes.
Right.
Now my question is above 2. Can you
Can you generalize that
No,
to
it's
a
not.
higher thing? Wait. If you count the passive lengths too, then can you boost?
I think it's known for hypergraph. You can modify some statement, but sometimes when you transfer to graphs by taking shadow, something goes wrong sometimes. So I'm not sure.
Yeah, that's a good question. Let's think about that. It seems like it should be, I think it should be easy to prove
Big
after
theta,
knowing
big
this,
theta.
to prove for every, I assume so. Okay, maybe I have 2 more minutes to answer his question, or we don't have the time.
Go ahead.
So he was asking extremal number of n. We count number of triangles. Sorry, we count number of triangles, and pentagon is forbidden. How does this look like? The structure looks like very easy structure. The graph, the triangles blocks are the following. Either all of the triangles share an edge in the one block. So I construct the block the following way. I start with the triangle, and then if there is another triangle sharing an edge with it, I add it, and so on. So this contains C5, so it's really rigid structure. So either they look like this, which are diamonds, or they look like K-force. So this is one of the structures. So now every cycle of length 4 is easy to see that they live either here or there. So that it cannot be the cycle of length 4 living in 2 different blocks under the assumption that every edge is in some triangle. If it's not in the triangle, I can remove it. So if I know that every edge is in the triangle, then every C4 should be a part of one of those blocks. So my goal is to destroy the as C-force. So if I destroy the C-force here in this way, and here, how many triangles we had? We had, does not matter how many, but for each triangle I have left one edge. So number of edges remaining after I even remove this edge is as many as triangles I had. Here, how many triangles I have? I have 4 triangles. So I need to destroy edges the way that I will not have any C4, so I have 4 edges. So if I do this, the graph with which I started had no C5. Now the graph which I got has no C5 or C4. And we know that the final graph contains at most 1 over 2 root 2 and to the 3 of edges. So this is symmetry. Therefore, number of triangles in the beginning was at most this much. So this was the proof, one of the proofs of an upper bound of this problem. And then this proof was sharpened once and then the second time, but still there is a gap, and I think there is some idea I have, maybe it will work, and we can try some other time. Thank you very much.